Welcome to the fourth section of the course. This section is called Optimization Heuristics. In the previous section, we learned about pathfinding in graphs and grids. We learned a new algorithm called Dijkstra's algorithm, which could find the shortest paths on weighted, directed graphs, and we learned how grids and mazes can be represented as graphs. In this section, we will see how we can optimize our pathfinding algorithms. We will learn about a concept called heuristics and see how they can help optimize our algorithms. Then we will implement a simple pathfinding algorithm that uses heuristics greedily. Then we will combine heuristics with the concepts from Dijkstra's algorithm into a new algorithm called A* search algorithm. We will implement A* search in grids, and finally we will see how we can optimize the search space even further by using bidirectional search. This video is called What is a heuristic? In this video we will talk about what we mean by optimizing. We will see what a heuristic is, and we will discuss how we can find good heuristics for our algorithms. So what does it mean to optimize? There are many things we can optimize. We can optimize our implementation to make it run faster by using more clever data structures or using knowledge about a programming language, such as multi-threading the algorithm. We can also optimize our graph representation instead of tweaking the algorithm. Remember in the last section where we could represent mazes as grids, but we would have a lot of redundant vertices in that case. So instead we optimized the representation to only have vertices in the junction and turns, which made the graph much smaller. Finally, we can optimize our algorithms so they find the desired result using fewer evaluations, by not having to inspect more vertices than necessary to find the shortest path. This is the kind of optimization that we will be doing in this section. And to do this, we will use heuristics. So what is a heuristic then? A heuristic is basically a guess or an estimate. When using a heuristic, we try to guess which action will be the best to take next, and if we often guess right, we only end up evaluating the correct vertices on the way to find the shortest path. If we instead are very bad at guessing, we might end up visiting many unnecessary vertices, thus slowing down our algorithm. In pathfinding, we want to guess where to go next in order to reach the goal fast. In chess, we could use a heuristic to guess which piece would be best to move in a given situation. The more information we have about our algorithm and domain, the more precise our estimates can be, which in turn gives us better heuristics. It might be valuable to spend some time looking at the domain before running the algorithm to gain knowledge about the domain. In this grid example, we see that the blue-colored area is enclosed by walls. If we want to move between two white cells in the grid, it will never lead to a shorter path by going through the blue area. So we might use this domain knowledge as part of a heuristic, which will prune this area from our search, thus leading us to inspect fewer vertices. In chess, we might use pre-computed lookup tables for heuristics. Chess is a very complex game, and it will take a lot of time and computing power to calculate all possible board configurations many steps ahead. A common technique in these cases is to start by searching a given number of steps ahead, maybe 5 or 10 steps, and then if no clear solution has been found, like a checkmate, we'll use a pre-computed lookup table to determine which moves to make. By having it pre-computed, it is possible to make quite good estimates, as the tables can be refined if new knowledge is acquired. In pathfinding, we usually use distance to goal as the heuristic. This doesn't take walls and other structures into account, but it gives a good estimate that makes our algorithms work well, and it is very cheap to compute distances. In this video we defined what we mean by optimizing, and we talked about what a heuristic is and how we can find good heuristics.